Hello, good afternoon. This is the last day of the CFD short course, Introduction to Modern CFD, and we're going to talk about environmental flows. So there's an increasing realization that the humans are having a drastic effect on the environment. Some have concluded that middle of this century will run out of physical and environmental resources. Now, the environmental resources can be put into two baskets, physical and biological. So the physical consists of earth, air, groundwater, and surface water. The bio, of course, consists of plants and animals, and they are under also great threat. So let's consider this. In this talk, we'll only consider the fluid part, that means air, ground, water, and surface water. So in the atmospheric field, there are two components. There is the wind field and there is the dispersion, right? So the governing equations are, of course, Navier-Stokes combined with, other supporting equations. Richardson was one of the first one to use and try to predict the numerical weather prediction. He had some 6 hours of data, and he forecasted for 6 hours from the data he had, and there was some validity to that. But the modern advanced models started after the advent of the electronic computers, and NCAR is one of the leading agencies in this field, and it works with other government agencies to maintain a state-of-the-art model that couples with atmospheric flow and ocean currents and greenhouse gases and aerosols and all those complex things. Many other countries and organizations have their own models, and each has some strengths or weaknesses that can be interesting. Now, let's look at the wind field. The wind field can be looked upon at many different scales. Okay, this is one of those multi-disparate scale problems. There's the global scale. For example, if you take the jet stream, it moves at the global scale. So if you want to predict that, you need a model that goes around. Then there is the mesoscale. Mesoscale is basically, something like thousands of kilometers, and it will be like size of a country. And then we can come down to the regional scale, hundreds of kilometers, like the state, and then we can get down to the city, we can get down to the components, and finally we can get down to our own level, like the human beings on the order of meters. So each has its own promises and problems and pitfalls. So we have to be careful at what scale we're working, okay? So typically what happens in these models is that you have a grid generation. The grid is typically, the terrain is very complex. And then also you have to take account the land use data. There is urban, agricultural, mountains, forests, and all those things. They have their own problems. So all they put it into the grid, and then you develop what is, which could be a mesoscale model. Then you also have a number of weather stations. Atmosphere is one nice thing where there is a lot of weather stations. There are thousands of them scattered around the world. Now they're providing you real-time data. Okay, so those are usually have to be taken care of to make sure your model can be validated against them. Okay, it's a complex problem, very complex sources, complex boundary conditions, and there are both Eulerian and Lagrangian transport models, and there's then aerosol is an animal in itself. Particle transport is a big problem and a big issue. Now let's look at the typical mesoscale model. Usually a mesoscale model would work have nested grids, because there may be places where you need more resolution, places when you need less resolution, so you'll do that. Now, but these mesoscale models do not work at small scales like 100 meter, 100 meter below that, okay? So they usually have much larger grids, okay? So at that one, we use what we call it here, I'm calling the G1 grade, which comes at city level. So here we have to solve by CFD. We cannot use the mesoscale model at this level, okay? So mesoscale model, though, provides the initial and boundary conditions. We'll come to that in a minute, okay? So the mesoscale models, typically, one of the most well-known was MM5, which is now replaced with the WRF. and then you have like TAPM, ECMWF, and then there are other ones. So these are typically non-hydrostatic nested grids, terrain following, and they have weather climate modeling, they're coupled to ocean circulation, they track aerosols, and they have very complex chemistry, turbulence, all those things. Okay, they're typically used both for research and for prediction of climate change and weather forecasts that you hear on the TV. Now the output is typically hourly at every grid node, and you get wind speed, pressure, temperature, particulates, and all that. Now, when we come to the CFD models, they are useful at a smaller scale, at these scales of 100-meter range, anywhere from a meter to 100-meter range. So they are, there are quite a few of them, right? Okay, or any CFD model basically can be used for that, okay? So what you typically do is you embed this model within the WRF in this case, within the mesoscale model, such as MM5 WRF, right? So then you extract the boundary conditions for that, and you put those boundary conditions into this model to drive this model, okay? Now, one more thing you do is that CFD models cannot go right down to the ground. There is a boundary layer, right? You remember from my turbulence lecture that walls, you don't go down to the wall because you need a very fine grade. There's a high gradient, same thing happens on the ground. So this profile is typically logarithmic. As we said, it's no different than any other wall. And so what we do typically is in these models is that we put in the values of kinetic energy, U and epsilon, etc., from these relations, okay? And so that is what drives the model in the atmospheric boundary layer, the ABL, as it's called here. Now, let's look at the ABL, which is a very important thing that happens. ABL is the layer of atmosphere next to the Earth's surface, characterized by a log law, okay? It's subject to daily variations from heating, sun, heat reflected by Earth's surface, humidity in the air, and all that. And the interesting thing is that the potential temperature drops with height, okay? And this means that if you're going above, the temperature is lower, okay? So the colder air is on the top and warmer air is at the bottom, right? Warm air is near the bottom. So this is called the lapse rate. Lapse rate is typically about 10 Kelvin per kilometer, okay? So this is what it is. So it's a colder air is on the top and it sinks to the bottom. And that's also what makes for good thermals. If you are a pilot, like I was in my younger days, a glider pilot, you're looking for the thermals that rise up from the ground, okay? And they do that because of the heat generating a buoyant plume above cities and things like that. So after a certain height, though, the temperature begins to increase again for a while, okay? Then, of course, it'll fall down to close to zero. But the height where that occurs, where the inversion occurs, okay? The temperature decreasing and then increasing is called the inversion height. So below that is the ABL depth. Typically, it's maybe 1,000, 2,000 meters in that range. So if you live up in the hills above about 5,000, 6,000 feet, you perhaps have less pollution than the one for people like us who live at the ground level in LA. So inversion acts like a lid. Most of the pollutants get trapped. There are some that escape, right? Like ozone, some of the chemicals, CFCs and all that can escape from here and destroy the ozone layer. But many of the others stay trapped. But I would say most stay trapped, okay? So what's the role of stability? What's the role of the ABL, the atmospheric boundary layer? It's related, as I said, to the vertical motion, because here you have cold air on the top, which sinks, and warm air at the bottom that rises, okay? So when the flow is going up, ABL becomes unstable, right? Okay, so when the flow is coming down, it's stable. When the flow is going up, it becomes unstable, very eddies form and all those things form. And stability is very important when you think of dispersion, okay? Dispersion is affected by stability. Under stable conditions, pollutants will not disperse much and they'll sink towards the ground eventually, okay? So it could be dangerous, of course, because it's undiluted and they settle in population areas. So the ABL, when it becomes highly turbulent or unstable, then of course it enhances mixing, and the mixing dilutes the concentration, which is good, but also the transport can be to longer distances when that happens. So in the dispersion, we basically say that transport and disperse, see how it works in the atmosphere, how long they go, where far they go, what are the concentration. That's what atmospheric dispersion is. So we need to find out the concentration in space and time. And there are two kinds of models. One would be predictive models and one would be inverse models. Inverse models basically say, given a concentration, what is its likely source of origin? Okay, so it's the inverse problem, which is very useful, for example, by regulatory agencies. Hey, I saw this high peak of SO2 or NOx or something. Where did it come from? Okay, and they can pinpoint the potential culprits. Okay, so that's what the inverse models are. Then, of course, both the inverse and the forward models or predictive models are used for establishing the effect of any plant, any accidental releases that might happen, like Fukushima happened, Bhopal happened. If we'd done studies of how to vacate the population before these happened, we would have been wiser. We didn't do that, but today there are a lot of effort being spent in doing these disaster studies to plan for these disasters. So you do a lot of these studies, hypothetical ones with assumed scenarios. Now, one of the things that comes to dispersion is the aerosol. Okay, it contributes to global warming. And then there is, of course, volcanic emission, geoengineering. So we have to deal with that too. So there are two steps to computing atmospheric flow and dispersion. First, we need the wind field. Okay. Now, if we are working at the mesoscale, we can use the flow computed by the WRF or MM5 or any mesoscale model, right? Now, when you're working at a local scale or a regional scale, smaller scale, city scale, building scale, then that is not feasible. WR doesn't have the data at that scale, okay? So there are two options. First and simple and effective, but not very accurate option is to use the measured weather station data, put it in the continuity equation, and solve the equation with certain constraints saying maximize, do me a least square minimum error with this measured data. Okay, that can be done with continuity equation and is done, and that's a first line of defense. But if you have the resources and you want accurate answer, then you have no option but to use a 3D CFD model like our model answer or Fluent or OpenFOAM or whatever you have. Once you have now the flow field, now you can do the pollutant dispersion. Okay, so that will be the dispersion models, the pollutant dispersion models. Now for these, you will require the topographic data again, you'll require the wind speed direction, stability, inversion height, release data, what is being released, when, where, how, what are the sources, and all those things that you need. So there are three kinds of dispersion models, two major kinds, which is the Gaussian Plumes. That's the first one. That's the mainly we know at certain analytical solutions under certain conditions, and that will be the Gaussian Plume. The other models are CFD based, and there are two types, Lagrangian and Eulerian. Okay, Lagrangian track individual particles in a flow, right? So the particles undergo various processes, but each particle is tracked. In Eulerian model, a transport equation is solved. So here is a quick look at the Gaussian Plume models. This is what a Gaussian Plume is. We say Gaussian because the analytic solutions for a uniform wind field are these Gaussian solutions that give you this plume, and it tells you how the concentration is. And then, of course, during certain conditions, such an application may have, for example, if you had a strong lapse condition, then this is what the plume actually looks like. So this will not be very valid. Now, when you come to the CFD models, these are much better for gas particulate transport and for complex sources in wind fields and all kind of variations. So the Eulerian models can also deal effectively with reaction, decay, aerosol dynamics, but Lagrangian models, on the other hand, have certain advantages. So let's talk about those. So the Lagrangian models are basically like a random walk kind of model. You say, I know the distance at a previous time. I'm going to add a random component to that, which is based upon to simulate the diffusivity. And then I'm going to add a velocity component based upon the actual known velocity, and I'll get the next location of the particle, right? So that's what basically a random walk model is. So it's there are different variations. Our model is called random, but there are a number of other models that do something essentially the same. They're conceptually very simple. They track particles of pollutant. There's no grader needed. They are truly gridless, and the wind comes from the wind model, so you don't need that. Okay, so they are inherently stochastic, and turbulence and atmosphere is inherently stochastic. They're very suited. And then they are very quick response situation, episodic. They are very good model to quickly see where things are going. Like something has happened, you have a short time to react. This is one of the best models because CFD model would take a long time. You'll have to build a grid and all those things. So also the plume location is generally much more accurately identified. There is no cell size restriction, okay? So also it usually predicts the extrema very well, okay? If you want the maximum concentration, this is perhaps a much better model than the CFD Eulerian models, okay? And of course it can one, but we cannot use this for reactive flows or chemistry. It becomes very expensive for that. The Eulerian model solves full 3D Navier-Stokes. We already went through that, and it's a determinist model, and it's good for local area simulation, flow behind a building, flow behind you if you're standing in the wind, okay? So it can account for chemical reaction, photography, aerosols, and many turbulence models and Eulerian ones, so you know all that, okay? So now the aerosol dynamics is basically very specific, and there are special models to deal with that. Okay, I don't want to get into the details, but believe me, it's a very complex problem. It's an integral differential equation. I mentioned that as one of the most complex problems to solve, but it's a very important problem. There are a lot of there is soot, there is dust, there is pollen, there are radioactive nuclides, and it's very important in many situations. So these partial differential equations take a long time to solve, but they can account for all these other things. So we have developed one of the most sophisticated aerosol models, which is being used for nuclear agencies, and we're waiting for the feedback to improve it with real life data. So here is a few case studies for you. What this does is it shows you the plumes developing. One is with a random Lagrangian, one is with a Eulerian simulation. You can see the difference in the shape between the two. The Eulerian looks more like, kind of a nice contours, but actually this looks much more realistic as to where it's going and what's happening with the wind. And you can see that the false diffusion is not there. At the last time, the wind had a high instability, and that's why it broke down. Okay, so this is the difference between the two. Now we come to the groundwater transport. So here the objective is to give you a basic understanding of the processes involved in modeling flow and transport. Okay, so the modeling can be conceptual. We have to do physical, mathematical, and numerical. It could be deductive versus inductive, and we need parameter estimation because ground is very special. Okay, we need to do calibration. Models can be for saturated, unsaturated. So I'll try to cover some of these in one. And of course, you already know that in these equations, things such as advection, diffusion, dispersion, retardation, complexation play an important role. A basic groundwater model basically solves the equation on the basis of a Darcy law. Okay, if the principal mass conservation is there, continuity is there, but basically the momentum comes from the Darcy law. Okay, so Darcy law, we'll look at it in a minute. It basically says that it's the difference in pressure that drives the one. Now remember that split between rotational and irrotational part of the velocity. In the ground, basically there is no rotational velocity. The friction is so high in these small pores that basically there is only the irrotational part left, which is dependent on the pressure. So the transport equations then we have for species conservation, which have to account for molecular diffusion and dispersion. In groundwater terminology, dispersion is basically what we would call turbulence. Of course, in this water, in the ground, water is a very slow speed. The typical Reynolds number is less than 10. So you can't really have turbulence. But you have a very similar process, much more complex process called dispersion. And we'll come to that. We'll talk a little bit about that. There is also, of course, a lot of geochemistry going on. Okay. So there's a lot of, if there's a decay of the species are decaying for many reasons. They could be radioactive, or they could be reacting with other species, or they could be taken up by some, amoeba or some bacteria, whatever it is. Okay. So these words you will hear, retardation, distribution, decay, and all these things that you hear in the regular CFD kind of thing. So let's look at the governing equations for these ones. The governing equation are the mass balance equations, transport of species equations, the pressure equation, okay, and the others such as thermal salinity equations, okay. So the constitutive equations are the equations which give us the soil saturation as a function of pressure. Okay, we'll come to that in a minute. And then there is things such as conductivity, storativity, dispersion. I'll see what I can address here. I'll give you some idea. Okay, a lot of physical processes going on, and then we need initial boundary conditions. So porous media is typically classified as porous or distributed fractures, okay, or porous and discrete fractures. So it can be either of those. If you look at the ground, it's usually a very complex kind of media, okay. So geometrically, it's defined. Then there are layers. Okay, there will be distinct soil types. Like if you dig down, you'll find that you first have some kind of a top soil, which is typically some mix of sand and clay and some broken down rock types. And then you go down and you might have a rock down there, or you might have an alluvial layer. You might have another layer, which is an underground river. Okay, so all those things happen. And so hydrologically, these are defined, these terms you hear, porosity, storativity, hydraulic conductivity, and things like that. Okay, details, there are plenty of information available in the textbooks or on the web. So transport is defined by both what I said, dispersion, which is like turbulence. It's not turbulence, but it's like turbulence. And then there is molecular diffusion, which occurs. Okay, so geochemistry and chemistry is also very important. Now let's look at the Darcy Law. So firstly, the fundamental equation describes the Darcy Law, essentially describes the saturated porous medium. Okay, so we have water in interconnected voids in the soil, and rocks may have fractures, so the water moves through that based upon the pressure differences. Okay, so ability to transmit and store this rock constitutes the hydraulic property. Okay, so Darcy was the guy who studied all this, and he came up with an equation which basically said the amount of flow is related to something called a hydraulic conductivity times the area times the gradient of the pressure. Okay, dH by d length. L is the length of the column. So you fill a column, a cylinder, or a column with sand, for example, you saturate it with water, you apply a pressure at one end, water would come out at the other end, and that it depends upon the gradient of the tube and the area, cross-section area, and something called hydraulic conductivity, which will be a property of the sand that you're using. Okay, so the porosity of a soil is a measure of the void spaces, right? If you look in the ground, you go to the beach, you take sand, well, it's not all solids. There are these grains of sand, in between there is trapped air, or there may be water, okay? So if you put that all together, you'll find X percentage is void and 1 minus X is solid. Now, no water can go through the solid, it can only go through the porous component, right? Okay, so the porosity is between 0 and 1, and more porous means that it's more, for example, pebbles, big pebbles would be more porous, sand, smaller grains would be less porous, the porosity would be smaller, okay? So the porosity basically is the volume of the voids to the total volume of the solid, okay? So it can be determined in the laboratory, okay? from what we call a bulk density and a particle density. Particle density is the density of the actual rock, and bulk density is the density of the mixture, okay, rock and water, okay, or rock and air. So unconsolidated segments, gravel, sand, silt, clays have larger porosity, typical around anywhere, typical would be 0.3, 0.4, somewhere in that range, usually 0.3 or so for agricultural soil would be in that range, okay. And then you have the crystalline and igneous rocks would have very low porosities, okay. They do have porosities, okay. No rock is absolutely watertight, okay. Just a question of how watertight it is. Basalt will have a lot of cracks and will not be that watertight. Granite may be more so if it is not fractured. The other concept is hydraulic conductivity or coefficient of permeability. It's the ease of movement of water through the porous media, okay. It's a, the coarse-grained and fractured material will have high hydraulic conductivity, and silts and clays, which are very tight, would have low values, okay. So it's a property of the geologic media, and also they can be anisotropy and inhomogeneity within a rock mass or a sand or a porous media mass. For example, in certain situations, water may run in one direction, like it may percolate vertically but may not go horizontally, or may go more preferably in the horizontal direction. That happens, okay. That's called anisotropy. Isotropy means like a typical sand would be isotropic because pores are equally distributed, random, and water can go any direction. But many rocks, for example, with fractures, you don't have isotropy. So this can happen. So hydraulic conductivity is a measure of that, okay. It depends upon the specific weight, rho times g of the which is proper density of the water, and depends on the viscosity, okay. So lower the viscosity, higher the hydraulic conductivity. Of course, this is viscosity of water we're talking of, water or air. So typically viscosities are fixed. So it basically comes down to how porous the material is and how easy it is to move, and that's called the conductivity. It will mainly depend upon the rock type and water properties we know. So the homogeneous and heterogeneous. Homogeneous means that the properties are the same everywhere, right? And if they're isotropic, that means, let's say in the 2D situation, that the conductivity in both directions is the same. The water can go in one direction or the other direction. In other words, if you have a heterogeneous anisotropic media, then you might find in this particular case that there is some reason for water to go preferentially in the horizontal direction, right, rather than the vertical direction. Okay? So that is anisotropic, and then it varies from place to place. So that means it's heterogeneous. So the word space can be composed of things like that, which is equivalent continuum, or it could be certain fractures in certain order fracture, okay, like this. That happens in the rocks, okay, that they fracture along certain fault lines. But then you can also have random fractures in the rocks, okay. So there are all these different kind of things. They're interconnected networks of all kind. So these representations will give you either a equivalent single continuum with average properties, or there may be two different continua, each its own one. For example, the fractures may be separate here. Okay, no flow can go, or very little flow goes to the rock. It's all going in preferential direction. Here it's going kind of anywhere. Here it's definitely going anywhere. Okay, so Darcy Law basically assumes that there's continuous smoothness, but it can deal with, we generalized it today to deal with anisotropic or inhomogeneous materials. Okay, and Darcy Law basically, if flow becomes very fast, much more than Reynolds number of 10, which is kind of considered the limit, and this happens in fractures. Like in fractures, sometimes the water can move very fast. So now a little bit of turbulence sets in, and we have to account for that. So flow is no longer laminar. So that also happens, and we have to bring in new terms in this, or we have to go to Navier-Stokes equations and put in special terms to account for the media. So some of the concepts are pressure head. Pressure head is basically the pressure divided by specific weight. In groundwater terms, you always talk of like let's say atmospheric. What is atmosphere? Of course, it's 14.7 pounds, per square inch, whatever it is. But typically we say, well, it's approximately, 34 feet of column of water, right? Or mercury, so much of mercury and mmg, millimeters of mercury. Okay, so we talk of the length or height terms, and that's because we divide the thermodynamic pressure by the specific weight of water, which is a good measure. And then, of course, the potential head means that we are above or below a certain datum. Okay, that's a term that is used, and that's always the term. We let's say compare to the ground, compared to the water pressure at the sea level, the pressure in Denver would be high. Okay, so that the water there also has a potential head because it's a larger elevation. Okay, then of course the water moves very fast. We have the kinetic energy. So this is what happens when, for example, you're hit by a fire hose. And of course, underground, typically, except in the mines or failure of mines, the kinetic energy usually is not a big factor, but it can happen. Okay, so we define a total head, which is the sum of pressure head, potential head, velocity head, and generally velocity head is negligible, as I said, but not always. So this is what basically is the total head that determines how the water flows from one point to another. Okay, so combination of pressure, potential, velocity, that is a good measure of the flow of water. Okay. Now, there is one more thing that comes in, which is the capillary pressure. When we have two immiscible fluids, air and water, it so happens that they form a contact surface, and there is a contact surface because of surface tension. It has a capillary pressure of its own. So the pressure is not equal on the both sides. It may be very small, but there is a difference. Okay, so that difference is called capillary pressure, and that small difference can be very, very important. Okay. So that makes, if there are two fluids, we get what is called a Vadose zone or an unsaturated zone. It creates an additional force because of the inherent surface tension, which creates an inherent pressure inside. And so it can even suck the water against gravity. Okay, that's how plants get gravity, because they suck it through the capillaries and they suck it through the fact that there is a Vadose zone below them. Okay, so of course, in saturated case, when there is only water, this has no importance. So there are two, or rather three kind of flows that I'm going to define here. There is steady state saturated flow, equivalent to heat conduction or Laplace type equation. Okay, that's what happens. It's elliptic in nature. We also have a transient saturated flow, which is parabolic in nature. And then, of course, the last one is the transient unsaturated flow, which actually works like compressible flow. It's hyperbolic in nature. You can show that. Okay. So here is the basic equation for a porous medium in transient form. This is the specific storage or term, which means how much water can be stored in one. This is like the accumulation term, right? So H is the total head here. Okay. So this is the change in the total head with time multiplied by the specific storage capacity of the one, which of course depends on the porosity, or for confined flow, there is other reasons why there may be storativity. And then these are the hydraulic conductivities, Kx, Ky, Kz. These are kind of the permeability of the water in three different directions. Okay, so the transient head. So for the steady state, of course, this term will drop out. Now, then the other important class is unsaturated flow, or variably it's called saturated flow, also called Vadose zone. So this means that two or more immiscible fluids are simultaneously present in the porous media. They kind of share the space with each other, like water and oil. Okay, then water and oil, water or air, and then oil and gas. And then, of course, all of three of them can be present together. We can have water, oil, and gas, which may consist of both oil and air and water vapor and gas and oil vapor, right? So, for example, the region immediately below the ground surface, air penetrates and coexists with water vapor and ground. Okay, because this is very important for agriculture. Okay, this is what gets the plants to propagate. Okay, a fully saturated region will not let the plants grow because they'll be like immersing something in water all the time, right? You'll be hydroponic situation underground. Okay, which could work, but I think generally it doesn't because not enough nutrient to get into it. So deep underground, oil reservoir with significant amount of gas may be present. So oil and gas is that, okay. Then there is something called artesian situation. Like you can go down in the water, you may find there's no water, and then you may find there's water. Why this happened? This happened because over the years, there may have been bodies of rocks which got buried. Sorry, not rocks, but the soil that got buried and formed layers, okay? So this will be, then the water flows through those because they have higher permeability, and these will be this is actually where most of the water is. These are called aquifers, okay? So these are typically places where underground you have large bodies where the permeability is high, and maybe the sea level rose, maybe there was something else that happened, and all that thing, kind of moved around and created these aquifers. So the governing equation for unsaturated flow, unlike the equation I showed you before, is called a Richardson equation. And that basically looks a little like this. You'll find two differences. There is something here, this storativity term is now become the pressure function of the capillary pressure itself. And then there's a buoyancy term that's added to the vertical direction because there is a natural buoyancy. So this is a situation here, there's air, there is water, there is solids, but actually there is a water throughout there. So this is not really a steep saturation. So we sometimes assume a clear layer between them, but usually it's a continuous saturation where the water goes from one here to zero at somewhere here. Okay, so air also has moisture in it. Okay, so both are used for modeling. I just wanted to give you an idea of the different things that happen here. So when it comes to unsaturated flow, there are two things very important. One is that the capillary pressure is itself now becomes a function of the saturation, right? You can imagine that you have two different fluids, water and air, right? So if there is a surface tension between them. Now, if you change, let's say, the saturation, you put more water, of course, the surface tension is going to change, okay? So if that happens, this is what the surface tension curve looks like, the capillary pressure looks like. As saturation goes very low, the capillary pressure rises and rises and rises by orders of magnitude, okay? So it's a very steep curve. This is 10 to the 9, this is 10 to the 4, and this is, only goes from 0 to 1. So it's a very curve, and there are different ways I've shown here, the Brooks and Corey, or the Brooks and or the Van Gnuchten curves, but there are many other ways in which this is defined. Also, what happened at the same time is the hydraulic conductivity becomes also a function of saturation, effective hydraulic conductivity, because we're talking about water, okay? So as you keep on increasing the amount of air, well, water is not going to move, it's full of air, right? So it's going to go down to 0, right? Or some very small number, okay? So these relations were developed primarily for agricultural soils with high porosities and may have their own problems. So I typically tell people, if field data is available for your situation, use it directly. If not, then use one of these curves, Brooks, Corey, Van Gnuchten, there's about 50 others. It's like the turbulence. Like I said, when we don't know enough, we have many models. Now, groundwater is highly stochastic in nature, okay? The soil properties, you just dig up in your ground in your backyard, you'll find all kinds of things, including the toys that your son buried 50 years ago. Well, if you're that old like me. So even if you ignore long-term geologic changes, okay, the media is stochastic itself, okay? The random holes, right? There's random connectivity. Just go look at the beach. And soil is very stochastic. Start digging and you'll find there are layers, there's clay, there's sand, there's rocks, okay? Initial boundary conditions are also very stochastic, okay? Again, just go down to the ocean. How are you going to specify if you want to do the groundwater flow near the coast? What are the initial boundary conditions? Well, they're changing with the sea, okay? Physical process is very poorly understood. Ground is not directly accessible to us. We can dig a hole, but then we only understand where the hole is, okay? Geochemistry is poorly understood. So all these things happen. So all these stochastic variables, we say we don't have a conductivity, we have a PDF for conductivity. We know what it might be with this certainty, okay? We have a probability distribution function, okay? We have a mean that may use, And we may have a standard deviation, but we don't know the exact value. So we have to use the best value. Quite often, we just use the mean. And quite often, we use the geometric mean in this situation because the situation is random. So typically, it's good to do, if you want a high confidence, you have to do a number of realizations. It's a highly stochastic process, similar to turbulence. Now, with that, with the time left to me, I'm going to move quickly to the shallow water transport. And shallow water transport is basically transport in coastal areas, lakes, and things like that. I'm not going to talk about the deep ocean, okay, where again, like the mesoscale model, there are different kind of models that are used for the ocean. They couple with the atmosphere, all those things happen. So I'm not going to talk about that. So let's talk of the coastal water bodies. Usually, there are three kind of problems that we have to deal with in coastal water bodies. Well, there is the tsunami and the storm surges, okay? And so I put them into two different ones because tsunamis and storms are essentially two different things, okay? Then there is the dispersion, okay? So the main objective in tsunamis and storms is to determine the high and low water levels, how much flooding occurs and where does the water recede. Now, best example of having not done that properly or taken that into account was the Fukushima and the New Orleans in 2005. So these disasters would not have happened if they had done and taken appropriate steps to model these hypothetical scenarios and seen what can we do if that occurs. Actually, it's quite tragic that there was a study done for New Orleans and it was ignored. Study basically said what would happen, and nobody took any steps to counter that because it's too expensive. To the cost, they said like some, I don't know what, 20, 30 million, and then they wound up spending $1 billion or something like that. The second problem is that of dispersion. Dispersion is because many industries and power plants are located near seacoast and lake shores. In some places, like for example in Saudi Arabia, much of the potable water, drinking water also comes from the ocean, okay? They don't have too much in their deserts, okay? Now, we discharge effluents in the water all the time, and they can have a significant effect. Every nuclear power plant discharges hot water, and there may be other plants that discharging chemicals into it, okay? So all these get in the water. Industry uses all kind of things, and they use the water for cleaning, for feedstock and all that, and dirty water is thrown back into the water body. So inflow from these water bodies can cause a big problem for us. And here we are again. So we must maintain a certain water quality both for the feedstock and for drinking. So what are shallow water equations? We already hinted that in the governing equation section. These are the water equations that describe the flow under a surface under given atmospheric pressure. Okay, surface is assumed to be at constant pressure. It separates the air from the water, right? That's what happens in the ocean. That's happened in off coastal water body, right? So the free surface, it doesn't have any shear in the water, right? Okay, but there is wind blowing across it. So that's another thing we have to take account. So when the surface is disturbed, it generates waves, right? So we have to deal with them. The shallow water is typically defined when the wavelength is at least 20 times the water depth. Remember when I said that you need at least 12 points to do a sine curve, right? So it's a similar kind of thing. It's not unusual that we find that order of magnitude. So 20 would define a sine wave very well. So a long wave means that it's about 20 times the depth or more than 20 times the depth. And then we can say shallow water equations apply. In open seas, depth is very large. So we cannot use shallow water equations. We have to use other equations. And I hinted that those are different models. So we are only going to talk here of the component that deals with the flow. There are another useful class of models which don't deal with flow. They only deal with the waves. You can do that also. And they are very useful for many reasons. But here we're only going to talk of the flow component. So what our interest for tsunamis is, and the same is for the storms, is that we are interested in the run-up height. How far does it go? What is the height at that time? Okay, so what is the inundation length? And if this is the sea level, this is the inundation length, and this is the height of water that is there at that time. So this is the extra water that we have to deal with at that time. Okay, so tsunamis can be caused by many things. It can be meteors. It can also be caused by storms. And then there are landslides that occur in the sea. There are landslides with a big piece of land, a rock falls into one that has happened and creates a tsunami. And then, of course, there is underground earthquakes that also generate tsunamis, like many instances of that. So here we're only going to discuss the depth average model. They are satisfactory for many purposes. They're a first line of defense. Okay. Now, when water depth becomes very significant, such as stratification, then of course we need full 3D models. Okay, then you cannot use a depth average model. So you have to look at your application. For rivers and small lakes, when depth, where there is a lot of things that can go on, full 3D CFD modeling is usually recommended in such situations. Okay, so typically the domain of interest for shallow water tends to hundreds of kilometers and 1 to 10 kilometer depth. That's where we typically apply them. The bottom, of course, is always the sea bottom. It's usually very rough, and our interest is typically in the surface levels, as I said, the water levels and thermal species concentration in the water bodies. So we can safely assume that in these shallow waters for these range, typically you can show theoretically that vertical velocity component is small. So it's not a bad assumption to use a depth averaging technique. And also the pressure distribution in the water column is hydrostatic. Okay, so there is not a pressure variation either. So it's a good assumption for many coastal water bodies. Now here is how we define. Typically, here is the sea bed, and here is the water level at any given time. So what we do is we take a datum, which is called the average sea level, and we typically define with respect to the datum, the total height of water at any point is this one. And the bathymetry depth, which is called bathymetry to the seabed, this is the seabed. And then we have above the datum, we call it eta, okay, which is basically the departure from this one. So this H is made of H plus eta. Okay, so this is basically eta is equal to total depth of water minus the bathymetric depth, right? So this is then the equation that comes in. It says that d eta by dt, continuity equation, says that the rate of change of height of this eta of the departure is basically total flux coming in, HU from one direction, total H is total depth, V, so total amount of water is equal to this, which makes sense. It's not different than the equation that we saw before. Convective terms, convective flux, accumulation, source. Now, when you come to the governing equation, because we average them, we still have the convective flux and we have the change in time. I've taken rho out because rho is essentially typically constant. We can take it to be. If there are changes in the rho, we can deal them in a linearized manner because the changes in water density are usually not very great. So a few percent usually. So what happens is that these are the forces acting on that water to change the gravity. First of all, there is departure of height, which is like a pressure that is created by departure of height. If the water is high on one point, eta is high on one point, low on the other, it's going to create a flow in that direction. Then, of course, the atmospheric pressure may have its variation. The pressure in LA may not be same in San Francisco. So the atmospheric pressure gradient would drive that. Then, because we are talking about large water bodies, there is something called a Coriolis force. Okay, this is the Coriolis constant. This is because the curvature of the Earth that imposes its own Coriolis force, right? And then we have the wind at the top. Okay, the wind is blowing at the top. So this is proportional to the square of the speed of the wind and a empirical coefficient and the direction of the wind. And then finally, at the bottom, we have the skin friction due to the roughness or friction at the seabed, right? The water is rubbing against that, losing energy. That's what this term is. And then, of course, there may be sources, we may be injecting, we may be withdrawing water and all that, okay? So these are the main forces that are acting on it, okay, all the time. And this is the basic equation. We saw this before. Now, what are the numerical methods? A water body is inherently time dependent, no steady state flow. Okay, so it's pointless trying to solve a steady state. There is no such thing, okay? And we are going to do a numerical scheme that must be time accurate, okay? Otherwise, you would lose track of the waves that are very important in distributing these heights. So shallow water equations can be shown to behave very much like compressible flow equations. The eta part just acts like a density variation, okay? So typical contemporary models have some kind of a Riemann-Gounod solver methods, but there are others. Lindersee had a very good method, which is still used a long time ago. But basically, these are becoming more prominent because they are compressible flow type of equations. So they basically can better propagate the discontinuities, okay? Now, auxiliary information needed for this computation is the tides, the bottom friction coefficient, wind friction, Coriolis coefficient, sources, intakes, outfall. And if we're doing dispersion, we need sources and sinks of heat and containment, thermal diffusivity, mass diffusivity, chemical reactions, and anything that connects to the bottom or the top. So for tsunami modeling, we identify the domain of interest. We use the bathymetric data. We assume typically for tsunami that wave is very small compared to the tsunami changes. So we can set it to 0. If we have the data, we can put the tide in there, okay? So we can then carry out the propagation of the tsunami over that. And there is 2 phases. One is tsunami, initial phase of the wave evolution, disturbance, and waves travel from the disturbance, flow speed is very large due to depth at time, okay? So the waves move at very high speed, okay? And, you know, you can't outrun these waves, okay, at that time, okay? So then you can do a run-up annunciation. So once they come close to the coast from open sea, the phase of tsunami when it reaches the shore is very important. And then that will determine what height you have at that time and what speed you have and what is the water level. It typically happens very quickly. And as I said, that it's so fast and the speeds are such that, you can't outrun these tsunamis. So the wave speeds, okay, waves to pass unreflected or open boundary, these are the boundary condition we use. And we say the velocity would be related to the height with this condition, which is the radiation boundary condition. The time step, because we want to maintain second order accuracy, usually there is a limit on the time step. So here is some examples. We did this modeling. I think I showed a little bit of that. And you have to get the whole bathymetry. So this is the depth of water at different ones. And we had to figure out the tide, wind condition, bottom friction, and there is uncertainty in all these, but it doesn't affect. So we can also say, how is the tsunami generated? Okay, is there fault like this? Okay, then did this part fall down on one side and on the other side that generated tsunami? So something like that. There are all kind of models. And then, of course, you may have data for a real one, but if you're hypothetical one, you can generate these tsunamis. There are a number of tsunami models. So this basically is a simulation. I'm not going to show you a video here. It basically gives an idea of the direction in which the tsunami energy is being transmitted, and also gives you an idea of the maximum heights, okay? So for example, the maximum height of the coast where it hit was on the order of somewhere around here, so about 3 to 5 meters. Okay, here you had waves which were like 12 meters up there, and you perhaps seeing about 10 meters here. Okay, now that's you can imagine 10 meters, like 3-story high building. Now, storm surge model is kind of identical to the tsunami. The difference is the surge itself is created by moving atmospheric phenomena. A hurricane, cyclone, typhoon, it's developing and it's moving. Okay, it's not a fixed thing that happened in the ocean like a tsunami. It's not a fixed location event, right? And so that's the main difference. So not only do we have to delete to cause with that, but it changes. So these things evolve. Cyclones can become stronger. Typhoons, cyclones, hurricanes, these all can become stronger depending on the conditions of the ocean and the atmospheric conditions. So the model needs to compute the tracks and where is the eye of the hurricane, how it is moving, and this location can move. So wind speed can be transient, spatially changing. Atmospheric pressure can be very strongly varying here. So you impose all that. So there are many models to generate, for example, these ice and the hurricanes. And this, for example, gives you how this is one model of Holland, which tells you how these things move and what happens to the hurricane. I come to the last stop, which is the modeling for the dispersion. So here we want to figure out what's happening to the water quality. Okay. Now, usually what happens is that we have an intake and we have an effluent discharge from an industrial or power plant, or because effluent such as treated or untreated sewage is discharged into the coastal water from a city, right? So these are the typical situations. So if depth is small and there is no vertical stratification, we can use shallow water equation. If, as I said, if there's stratification, we have to use 3D models, okay? So if stratification occurs, or significant depth variation occurs, then we must go to 3D Navier-Stokes, which we already talked about, okay? But the resources for 3D will be considerably more, maybe 2 to 3 orders of magnitude in computer time, okay? So don't forget a 2D, because in 3D, you'll need at least, let's say 100 grades on top of that. That's only 2 orders of magnitude. Then the total computation would go up, matrix with slow convergence. So you could be in for a surprise. So near a source, there would always be 3D variations, right? But if you go away from the scale of interest, 10 times the distance of the source, the source may be very small, a meter pipe, right? So if you go 10, 15, 20 meters, you'll find that things are mixed. This is mixing. And the diffusion ensures that the vertical water column is well mixed. So for many situations, depth average models work. So we require the 2D or 3D flow computations. We need the source of the effluent. We need boundary initial conditions, thermal mass diffusivities. So here is a typical component of a dispersion model. This is our model title. We have the heat transfer, convection, conduction sources, heating, atmospheric loss. We have mass transport, convection, diffusion, chemical reaction, biological exchanges, regeneration, assimilation. All these things happen. And the fluid flow, of course, has wind stress, bottom friction, and all those kind of things. So here is an example of what happens near the city of Dieppe. We did the Dieppe, where we did the simulation, and the tide is typically there's a bidiagonal tide. That means the tidal cycle is 12.5 hours. And you'll find that the flow would go up, flow will go down, and you'll see that the flow from the old time is stay there. Okay, this is the flow from the older cycle, the previous cycle that went up, coming back here. Okay, so the tide is moving this way. The tide reverses, it's moving this way. So the main problem here is to figure out what concentration is and not draw cleaning water from where the pollution is high. So that's what the basic situation is. Another quick example is that of we did a work for the King of Jordan, where we designed a private marina for him. I won't tell you what the advantages of flying first class in a private plane are. I didn't do it, one of my colleagues did it, but that's what happened. And we have here the computation of the water circulation. Okay, looks like time is up. So this is the water quality, and it tells you that what happened to the water quality. He was concerned about cleaning this up and having clean water. And finally, Navier-Stokes equations are one of 7 math problems that can earn you $1 million in one go. I'm an engineer, not a mathematician, so I didn't earn the million from that, but I just did CFD, and money is not the only measure of life, I believe, and I think I can tell you at my age, fun and challenges and having a good problem to solve are much more important challenges in life. I had a lot of challenges, a lot of fun. CFD is fun. Thank you very much.